So let's continue. Um, Today, the main subject of our lecture is geodetic support of construction. Well, first of all, it should be noted that um, we use different geodetic techniques in all life cycle of building construction. You probably know that cycle of building construction can be divided into several phases, each of which has its own unique characteristics and challenges. The following is a general overview of typical life cycle of a building construction project. Planning and design phase. This phase involves the conceptualization of the project, development of the design, and the identification of potential challenges and its opportunities. During the phase, architects, engineers, and other professionals work together to develop detailed plan, specification, and cost estimates. On this stage, um, we use detailed geodetic survey of the territory. And we must understand where, particularly in what place, the building should be put. Pre-construction phase. This phase involves the pro-document of necessary permits, acquisition of funding, and finalization of the project scope. This phase also involves the selection of constructors and subcontractors, negotiation of contracts, and scheduling of construction activities. Uh, Construction phase. This is a phase where the actual building construction takes place. It includes the mobilization of equipment and materials to the site, excavation and site preparation, foundation construction, framing, electrical and plumbing installations, and other construction activities. This phase is typically the longest and most resource-intensive phase of the project. Uh, on this phase, geodesists uh, making very important work of setting out the project in the particular position. And after each after the construction of each level of the building, geodesists are making so-called second survey. Uh, so this survey helps us to understand if the position of every brick of every part of building in the project place, in the proper place. Fourth, post-construction phase. This phase includes the finalization of construction, testing, and commissions of building systems and occupancy of the buildings. It also includes final inspection and certification, as well as any necessary repairs or renovations. On this post-construction phase, uh, the building can change its position in the space. For example, it just move down, not very on not very big distance, but maybe few centimeters, 2 or 3 or 5 centimeters, and geodesist uh, makes so-called monitoring, uh, geodetical and geotechnical monitoring of the building. and operation and maintenance phase. This phase involves the ongoing operation and maintenance of the building over its lifespan. It includes regular inspections, preventive maintenance, and repair or replacement of building system and components as needed. On this phase, geodesists also uh, makes the work of so-called geodetic monitoring because uh, we have different kinds of these deformations that can take place because of earthquake, because of landslide, because of vibration, or any another case. Nowadays, mm, when the war conflict in Ukraine is continuing, we also need to make an expectations of buildings that has had damaged by um, different weapons. And the phase, um, last step is demolition and disposal phase. This phase marks the end of the building's lifespan and involves the dismantling and disposal of the building's components and materials. This phase also includes any necessary environmental remediation and restoration of the site. Overall, the life cycle of a building construction project is complex and involves many different stakeholders and processes. Surveyors and the special data that they collect are present present are critical to the successful planning and completing of civil engineering projects. Surveying and its importance to civil engineering cannot be overstated and plays a vital role in areas such as, first of all, identifying and establishing property boundaries, collecting spatial information about a site, producing paper and digital plans of their spatial data, ensuring sites are built to design and within construction tolerances, completing as constructed surveys of the completed project. Accurate and reliable surveys are essential to prevent costly errors in a project and are uh, crucial for a smooth project. Um, Here in the picture, a total station is being used to survey the structural steel and crane rails on site. Surveying in civil engineering projects, well, surveyors are critical to a variety of civil engineering projects. The types of the projects that would require a surveyor throughout the duration of the project include roads, bridges, railways, tunnels, pipelines, dams, ports, utilities, and building foundations, etc., etc. In the picture, you can see a total station and the crosshair of the telescope of this equipment. You can see uh, principal points on on the bridge, and here we can um, calculate the coordinates of these points and understand if the bridge stays still or it has deformations. Modular structures and bridges. Set stakes, nails, or other devices to control the location and elevation of the various parts of the structures and progressive phases of construction. Provide horizontal and vertical control of all elements of the structure construction. Stake drainage facilities, electrical conduits, water and sewer pipes, pedestrian and bicycle facilities, traffic signals and sign supports, illumination devices, and other items shown or identified that are to be integrated into the construction of the structure. Uh, Identify marks or provide field notes or reports to the resident engineer. Such provision of information shall be adequate for the research engineer to review the location and elevation of the mark for the intended purpose prior to incorporating material that is based on the mark. Uh, Substructure. Uh, we should make stake reference or otherwise identify locations, orientations, and elevations necessary for the placement of substructure components, including but not limited to cofferdams, pilings, drilled shafts, footings, columns, abutments, caps, cross beams, bearing devices, temporary support of false work and excavations and embankments associated with any of the above. Verify and document the locations, elevations, and spatial relationships with adjacent substructure components. On bridges where prefabricated beams will be used, measure and document span lengths between devices at each beam location as soon as practical. Supply a copy of such documentation to the resident engineer for review before the next stage of construction. Superstructure. Stake reference or otherwise identify locations, orientations, and elevations necessary for the placement of substructure components, including but not limited to beams, girders, diaphragms, earthwork restraints, deck, rails, structure-mounted traffic control, and illumination devices, and concrete forms, temporary support and false work associated with any of the above. Stake alignment of structure as needed at each stage of construction. Stake alignment of uh, boarding place items at 10-foot stations or as established by the resident engineer. Here you can see in the picture mounting the targets on a bridge. On a bridge. Uh, and here another type of target um, that allows to control the position of a bridge. Bridge and deck grades. We set stakes or other devices to control the deck grade elevations. The exact process will depend upon the type of deck and the equipment being used. Control of a Portland cement concrete deck may involve significant work with the deck placement crew to establish control for a deck finishing machine. Rails for supporting the deck finishing machine are generally set up on either side of the deck. Each rail is held up by adjustable support every 5 feet. adjust the rail at each support to the desired grade while the rail is supporting the weight of the finishing machine. Control of an asphalt concrete deck will not generally involve as many variables as Portland cement concrete. As asphalt concrete deck surveys as wearing surface but not structural component. Asphaltic concrete will frequently be used as filler to create the desired super elevations when the flat beams from the superstructure. Stay control of the finished grade like any asphalt finish grade. Under some circumstances, design camber and structural deflection may need to be considered. Checking. Sufficient independent field checks must be made at the discretion of the resident engineer to assure the integrity of the construction stakes. The integrity of radial stake-out set-up points should be verified before use by making check measurements from other control points and measuring the distances between set points. All positions staked in the field should be checked against the computed positions and the results recorded in electronic stake-out reports and or on stake-out listings. Field notes. Construction survey field notes in the form of electronic stake-out reports, stake-out listings with actual staked positions noted, or suitable forms will be filled with the resident engineer upon completion of the survey. The resident engineer will provide copies to the contractor upon request. Machine control guidance. Machine control guidance technology uses position devices alone or in combination to determine real-time X, Y, and Z positions of construction equipment and compare that position against a 3D digital terrain model. A computer display shows the operation of grade checker several perspectives and delta values of their position compared to the design surface. This technology has the potential to increase the constructor's efficiency, productivity, and reduce the number of survey stakes required, thus reducing the number of construction working days. The construction industry is currently implementing MCG, and the department has developed interim guidelines to foster its use. Here you can see example of Topcon corporation equipment that is like a small screen, like small laptop inside driver's cabin, and every part of machine has so-called GPS trackers that precisely that are getting precise coordinates of every part of equipment. You can see another picture. So MCG may require a higher density of control monuments than needed for conventional methods. Setting additional monuments for machine guidance is part of construction staking. The constructor must utilize and constrain to the provided project survey control points for the digital terrain model. DDM and construction equipment locations too much. GNSS satellite signals can be subject to interference from canyons, buildings, trees, or even fencing and power lines. Additional monuments will be set when needed for adequate site coverage. Not all locations are suitable for MCG techniques, and it is the constructor's responsibility to determine if the site conditions are practical for MCG. Robotic total stations, guided equipment such as paving machines, uh, require a more dense survey control network or a higher order of vertical accuracy than GNSS controlled systems. Control should be staggered on either side of the highway to provide a good strength of vision. Typically, the distance between control points set for MCG should be no farther than 650 feet. The actual distance may vary by the type of equipment used by the constructor. The instrument setup must obtain vertical accuracies within plus minus 0.02 feet of the existing control. As-built surveys, as also commonly referred to record drawings, provide formal documentation of exactly how a project was installed. They document the actual result of the construction project rather than the planned layout shown in the project design and are critical for project closeout. As-built surveys ensure the project was built to meet the specification in the original plan set. This allows the project engineer to confidently sign off that the project was installed as per the plan. If any deviations from the original plan were approved during the construction process, the as-built survey will show the changes and they were installed and provide an opportunity to formally document those changes. Final payment to the constructor is also typically withheld until engineer sign off on the as-built survey. The as-built survey also provides a formal record that can be used to standardize how a project should be maintained over its lifespan. In the event of these stormwater ponds, accumulated sediment and debris should be periodically removed to achieve the original design depth in order to ensure the ponds continue to function at maximum efficiency. Depending on the type and scale of project, multiple as-built survey may be completed throughout the construction process to confirm critical elevations and layouts are being met prior to approving advancement to the next construction step. They are typically shown as an overlay on the original plan sheet to allow a direct comparison and easy identification of any significant deviations from the original plan. In the picture, you can see engineer with his with work. Probably they are making as-built survey. So as-built survey is check how did the construction phase finished. Is the every coordinate, every point's coordinate are mm, equal to the projected coordinates. Here you can see example of as-built survey um, documents, uh, pond outlet detail, pond inlet detail, and you can see as-built elevations, as-built flexant boundary, as-built outlet elevation. Area under bridge was not graded as part of this project. The outlet cross-section narrows in this area but remains unchanged uh, relative to the pre-project conditions. In order to keep the department's assets database current, a complete as-built must be submitted at the end of the project. The as-built will be collected during the entire construction phase in order to capture all features on the project, both above and below grade. The as-built shall be collected to accuracies shown. Um, Standard survey codes will be used on all department projects for as-built collection. If a code is needed that is not included in the standard survey codes, it may use but must be noted included civil XIN file which included feature definition and assigned symbology. Items that will be required in the as-built will include but not limited to all assets that are exposed below grade, exposed utilities, drainage, and other pertinent features as determined by the resident engineer. Above grade assets, curb and gutter, roadway slope, pavement section, roadway crown, sidewalk, uh, driveway locations, barrier, guardrail, and other pertinent features as determined by the resident engineer. Everything that is included in the design files and any additional supplemental items added or anything that was discovered during construction. All files must be named and placed in accordance to the standards. As will survey shall include a discussion of control used, measurements completed, computations made, and accuracies attained. The survey support shall become accompanied by all field notes used in the survey or printouts or electronically recorded field notes. The as-built survey must be of sufficient accuracy for the intended purpose of the project as discussed during the preliminary meetings. The as-built survey shall be collected to survey grade accuracies and shall be signed and sealed by the professional land surveyor who supervises the work. Um, the following files shall be included: original field data, file describing the basis of survey elements and datum in accordance with department standards, file containing original field survey notes or raw field data when obtained with data collectors. The raw data is a native data collector format. For example, DC, RINEX, ASCII, or DAT file format and log sheets must also be preserved for future retrieval. Cleaned up topographic as-built survey in DGN format or other compatible format as approved by the technology advancement engineer. The topographic survey should be free of any code errors and all backlines and featured connections and not overlapping. All features, line work, cells, and text need to be scaled based to U.CAD standards. Any additional created cells need to be included with the deliverable in a microstation cell library, for example, if you use Bentley software. Uh, the files must be named according to standards and provide also the data needed to ensure the as-built 3D model can be generated, including all assets or directed by the technology advanced engineering. Well, let's see some of the key benefits of having accurate surveys done on the above project include. Well, uh, let's make small break and continue after the break of 5 minutes. Well, some of the key benefits of having accurate surveys done on the above projects include, first of all, spatial data. Accurate spatial information is critical throughout the lifespan of civil engineering projects. Cost savings. By providing accurate spatial information or by setting out features correctly to design, surveying can help projects avoid costly mistakes and any reworks. Increased safety. Surveys can help identify high-risk areas such as live underground services. Having accurate surveys of what is uh, buried beneath the ground is vital to the safety of site workers. Compliance. Accurate surveys are the best way to ensure that the project is built as per its design and engineering specification. Here you can see in a picture a beta survey was completed to ensure compliance with standards before shortcut could go ahead. Role and responsibility of surveyors in civil engineering. Surveyors play a crucial role in civil engineering process. At the start of every civil engineering project, a surveyor will do an initial site counter and detail survey which will be used by engineers to design the project, which will be capture features such as the existing natural features of the site, the existing constructed features of a site such as roads, communications, and electrical utilities. Surveyed property boundaries. After the initial site design and planning phase, the surveyor's involvement in a civil engineering project will be setting out the design of the project to assist machine operators, traders, and other professionals to do their work as per design. Both during the project and once the construction works are done, a surveyor will then survey all the above ground and underground features as a record of what has been built on a site. Here you can see survey prism on a tripod is being used to establish survey control. Survey instruments used in civil engineering. There are a range of instruments that are used in civil engineering projects depending on the task being done and the accuracy requirements of the task. First of all, total stations. The most common surveying instrument that is used in civil engineering projects is the total station. Total stations combine the functionality of a theodolite and electronic distance measurer. They are able to precisely observe and measure horizontal and vertical angles and slope distances. The usability of total station increases when used with a survey controller. Survey controllers have applications that can set out points and lines and surfaces on the fly in the field. They can also measure and store points which can then be shared with other professionals who would use the data. Another kind of equipment is real-time kinematic global position system, RTK GPS receivers. RTK GPS is a fast and convenient surveying instrument that can set out and record points in the field, but is not as accurate as total station. RTK GPS receivers are suitable to use for bulk earthworks or for tasks where there is not a need for points to be stored or set out with an accuracy of less than 20 to 30 millimeters accuracy. The benefit of using RTK GPS over a total station is that you don't need line of sight to an instrument to measure and store points, as long as it is able to see a sufficient number of satellites in the sky, then it is able to work. Here you can see in the picture RTK GPS receiver is being used to establish ground control points for an aerial survey. This white figure you can see on the photos or on images that then will be get by drone or by airplane. Well, speaking about all the life cycle of a project, we just need to make attention to three main subjects. First of all, geodesy. The establishing of good or suitable reference systems for the project, geodetic surface reference network, and gravity field model. Gravity field model is necessary for correct recalculation geodetic heights that gathered by GPS receivers to the normal heights. So we just need to know the local geoid surface and difference between ellipsoid and geoid in the particular area. The next step is geodetic engineering. We make control baselines for azimuth and distances, instrument control calibration and test facility. You can see in the right of the picture, you can see a laboratory for instrument calibration, mathematical modeling, and precision surface to tunnel transfer technology. If we working for underground tunnel construction, and civil engineering project. Civil engineering invitation to tender documents, contributions and controls, geodetic transformation software development, integration of civil engineering monitoring sensor in survey reference network. All the geodetic infrastructure work is shown in the picture. Here you can see, first of all, key words and key phrases of the process. Invitation to tender, hiring, market surveys, site location, specifications, technical design, analysis, software application, data management, commissioning, measurement compliance, land access, calibration of instruments, reception, installation, controls, testing, construction, development, mathematical modeling, prototypes, and procurement. Well, geodetic preparation of every project is performed in order to obtain the necessary geodetic data during the execution of planning works on the placing of the construction project to the site. To do this, for example, the coordinates of the two extreme points of the main axis of the design structure closest to the geodetic reference points are graphically determined on the master plan. This can be done using AutoCAD, for example, if the topographic basis of the project and the project itself is loaded into the program. According to the coordinates, the directional angle or azimuth of the axis is calculated and the distance between these points in accordance with the design distance is specified, and considering this, the coordinates of one of these points are recalculated. Next, having the coordinates of the specified points of the structure and the coordinates of the points of the external planning basis, the planning elements are determined, according to which 2 points of the main axis are taken out from the geodetic points and fixed on the ground. In the following time, using working construction drawings, according to the corresponding horizontal distances between the axes and angles, the other main axes of the structure are taken out and fixed on the ground. Here you can see the principal schema of a building before it construct. The every axis, main axis of the structure with geodetic points, you can see. The direction of this axis must be parallel to the future building. So the coordinate system of the site, of the building site, is different from the state geodetic system. It has some control point to get reference with the world geodetic system or state geodetic system, and it has angle of rotation of this particular coordinate system. From the fixed axis, the contour of the pit and its arrangement, construction of the basement of the structure are planned. Then there is a transfer of axis of construction from axial geodetic points on a circle and overlapping of the basement with the use of theodolite or total station. Here you can see transfer of axis of a construction on the basement floor, and on the mountain horizon. Transfer of access to prefabricated horizons in the case of construction of building up to 9 floors can be performed by the method of inclined design using theodolite. From the main axis on the mountain horizon, the planning of the mountain axis is performed, from which the building structures are taken out. If the structure under construction must have more than 9 floors, then the basement floor is equipped with points of the internal planning base, which are tied to the main axis of the structure and transferred to the mounting horizon by vertical design devices. These vertical design devices, here you can see special holes in the floor of every level, and transfer of access to the mounting horizon by vertical design devices. To the technology of transmission of access, where 1 to 5 are points of internal planning basis. 2. Vertical design device. 3. Zenith hole in the flooring. 4. Is palette. So you can see here another pictures that explain how does it work. Here you can see an example of vertical design device. It has a liquid compensator. So, while the bubble of the level in the 0 point, so you can see in the lens and project the axis of U uh, reflects on the angle of 90 degrees, and you can project the position of the axis to the upper floors. Here you can see another examples of Zenith instruments. It's Chinese equipment, South ML 401, and another ZL 200. On the mountain horizon, where the point is transmitted, a coordinate palette is placed on plexiglass fixed in the metal frame of a square anti-aircraft or Zenith hole made in the ceiling of the building. The grid of the device threads is oriented parallel to the grid lines and on the pallet scale, and the vertical position corresponds to the average samples A and B on the pallet. The device is unfolded in azimuth to set horizontal stroke of the grid of grids to a position parallel to the grid lines and count along the palette lines with an accuracy of 1 millimeter. Next, we should turn the device by 180 degrees and take the second count, second count, taking the first position of the device as 0, set its position to 90 and to 270 and carry out on another palette scale counts B between 90 and 270 degrees. The vertical line on the palette is obtained as a result of the intersection of two perpendicular lines of the palette. And we use this formula. The transfer of the planet position of these points on the mountain horizon is performed by the method of vertical design with fixing the position on the two coordinate palette. From the received points on the assembly horizon, the planning of assembly axis of the building is carried out, and from them building designs and the equipment. Analysis of use of traditional geodetic technology shows that fixing on the ground of each of the axes with a pair of geodetic points on both sides of the building is almost impossible in a modern city due to the limited space of the land provided for construction. Part of the geodetic points is lost in the construction process due to the movement of various mechanisms on the construction site. And planning access on mountain horizons requires additional time which shows down the place of construction. Well, tolerances. Tolerances stated for each type of construction stake in this indicates the acceptable deviation of the position of each reference point from its computed position relative to the given alignment and grade. When the stake is positioned within its tolerances, it is deemed good. Staked positions are generally checked using the electronic stake-out reports, and if within tolerances the stated position is accepted. For precise measurements such as structures, reference points may also have an accuracy relative to each other. Tolerances should not be confused with accuracy standards. Accuracy is a function of the random errors associated with the survey methods and procedures that are used for the whole survey project, including project control, construction control, and the construction survey setup points. For construction surveys, survey accuracy standards indicate the expected variations in positions based on random errors for the setup points, not variations in the construction stakes themselves. And here you can see horizontal and vertical construction staking tolerances in decimals of a foot. Well, here you can see the structure survey control stations. Structure survey control stations we use a minimum of 4 control points for establishing the structure control network. Additional points may be set as needed. However, use the smallest number of original project control stations as is practical for establishing positions and reference points for the construction on the structure. We use control stations that are as closely related mathematically as practical. The contractor may establish additional control stations as necessary to complete the survey work. Additional control stations shall be established in such a manner as to provide the accuracy needed to meet the tolerances. Construction staking tolerances use structure control once established, independent of other project controls for the duration of the structure construction. Original project control station shall be used only after the following evaluation is completed for each structure. First of all, supply a list of the original project horizontal and vertical control stations intended to be used by the contractor in establishing positions of given structure. Measure relative positions of the original horizontal and vertical control stations intended to be used. Supply horizontal and vertical measurement data to the resident engineer upon request, and compare measured values with those computed from the original horizontal and vertical networks. Any discrepancy of consent to either the contractor of resident or the resident engineer will be resolved before the combination of control station is used. Here you can see the prisms that we use for line measurement. These prisms are mounted on the railroad to check its position, horizontal and vertical position, using total station, for example. And here you can see another examples. Control points are established, managed, maintained, and replaced by surveyors and created at the start of any development of civil construction project. Surveying control points are very important, and once established need to be protected from being damaged or disrupted. If they do get disrupted and moved from original surveyed position, new survey will need to be completed to re-coordinate new position. Here you can see in the picture destroyed permanent survey control mark that cannot be used anymore. How to decide where to place survey control point stations? When surveying new control on a site, the following should be considered before deciding where to place them. Will it be clear of future works? Is it accessible? Are there going to be any obstructions placed around the control mark, like fencing? If you are going to place a GPS base station on the control mark, are there any GPS window obstructions? You won't always be able to put in the perfect marks when installing new survey control. Sometimes you will place survey control knowing that it will eventually get destroyed. But if you consider the above list, then that should assist you in deciding where to place your survey control. In the picture you can see gray building. Red triangles are its mark existing survey controls, and new survey control are these points. How does it work? We should make 3 steps. First one, first of all, step your total station on existing survey control point 101. Set up targets on existing point 100. Set your backside to the point 100, and then turn and measure point 200. Then we should move total station to newly surveyed point 200. Then set up target on the existing control station point 101 and new control point 201. From point 200, we set our backside to point 101 and then turn 2 and measure point 201. Next step, move total station to newly surveyed point 201. Set up targets on the new control station to point 200 and existing control point 202, 102. From point mm, 10, set your backside point to 200 and then turn to and uh, do a check measure to point 201, to 102. This is a very basic example, but it highlights the steps needed to establish new survey control from an existing network of control stations. Another question, how many survey control points need to be established on a project? There is no rule for how many primary or secondary control points you need to have on an object. You only need as many survey control points as you need to be able to complete your job. It is best practice to have more control points than you need in case any marks get destroyed. If you only have the minimum number of control points and one get destroyed, then you are not able to complete your work. There are types of control points. Surveyors use many different types of ground control points depending on the circumstances of each job. Not all control points are as stable and long-lasting as others. Uh, Below, we can see on the next slide, we can see a list out of what I consider to be primary and secondary control points. Primary control points, first order, are what I would consider to be long-last points and to be used when establishing secondary control points, second and third order points. Secondary control points are not as long-lasting and stable as primary control points, but they are important to project and, if positioned correctly, can last a long time on a project. A good ground control point is one that is visible and usable for surveying and set out on a site and is stable and reliable to use. Primary survey control marks first order. What are primary controls in surveying? Primary control marks are usually a more stable type of mark and involves more labor to build and measure. Primary control marks that I have used on project include a brass plug set in concrete, mini mark set in the concrete footpath, deep driving steel rod, and a concrete pillar, either set in a steel pillar driven into the ground or a concrete pillar cast in a place. Secondary marked survey control point, second and third order. Secondary control marks are more temporary in nature and can be more easily disturbed. Types of secondary control include screws, nails, or bolts in concrete curb or footpath. Reflective stickers placed on fixed structures and nailed in a bitumen road. You can see examples of the survey control marks. And cadastral survey control marks. The types of surveying marks used in cadastral surveys are wooden pegs to mark the boundary, nails, screws, or drill no holes in concrete curb, or foot pies, uh, lured iron pins. And another kind of survey control marks are aerial survey control marks. Aerial control marks are usually checkboard style. The intersection of the checkboard or triangles as below is what the surveyed point will be, and when the aerial surveyor is identifying the marks to register from their photos, they will be able to easily click the pixels that match up with the middle of the checkboard. Uh, Frequently asked questions. What is the difference between a control point and a benchmark? A control point is a mark or monument that has a known horizontal and vertical position. A benchmark is a mark or monument that has a known vertical position only. Control points that have a suitable accurate vertical position can be used as benchmark as well. What is a control survey? A control survey is a process of establishing survey control points that can be used to provide surveying services on a land development or civil construction project. What are the types of control networks in surveying? There are two primary types of control networks in surveying. First, site control networks, and two, geodetic control networks. Surveying techniques used in civil engineering. The different types of surveys and survey techniques we use. Boundary survey. One of the first and most important surveys on a civil engineering project is the location and the identification of the property boundaries of the project. If the construction of a project goes outside of the property boundary, unless agreed upon in advance, it will likely result in expensive reworks to correct the error. Control survey. To be able to complete work accurately and quickly, surveyors need to have multiple control points collected around their work area or site. Control surveys establish the control of a project. And set out surveys. Set out so that the project is built as per the design. A surveyor will calculate and set out the design points needed on a civil engineering project. Speaking about um, accuracy of the work, we should remember the root mean square deviation. And I will share with you the file that explains all the peculiarities of the term standard deviation and RMS used in surveying. It is an article from our colleagues from Australia, from the Australian Surveyor magazine. And here you can see all the explanation needed for understanding the mm, standard deviation and root mean square. Uh, Here you can see all the formula and so on. Uh, And finally, we have 5 or 7 minutes. Um, I will show you methods of set out surveys. Polar method. We have A and B known points, and then uh, our equipment is oriented to the north or to the known points, and then we measure beta angle from the point A and the distance s of line AC. Uh, Another method is here you can see the um, tolerance and mistake of the setup of point C. While we set up C1 point instead of C, we have two different part of mistake. Mistake caused by distance measurement and mistake caused by angle measurement. Uh, so this linear dimension of this mistake you can see use the rho constant to recalculate it from angular rectangular coordinate method. We have so-called building grid on a side, and then we measure delta y and delta x uh, lines, and then we can set up C point in the proper place. Stripe method. Here we can use only angular measurements, beta 1 and beta 2, and we found point C on the ground using two theodolites. Mm, if we have no total stations, this method is also not so convenient. We can check the accuracy of our work uh, by measuring the angle y from point C, and the sum of all these angles, beta 1, beta 2, and y, and gamma, Greek letter gamma, should be 180 degrees. Create methods. We have points 1, 2, 3, and 4, and to create lines. And we can't find the C point in the middle. And creative linear serif method. We can find the point on the creative line between point 2 and 1, uh, but we should use the distance d to mark this point. Linear serif method, when we use only tapes, for example, we measure the distance AC and BC and found where the point C should be. So-called free station method. We put our total station in the middle between points A, B, and D with known coordinates and measure the angles uh, between the directions from C to A, from C to B, from C to D. We have also small uh, non-correct position, and we just can control this position using the force direction. When we use not theodolite but total station, this free station method is very popular because we can put our total station in the site, just orient our total station to line A and to line B, for example, and to line D, and then the total station calculate its coordinates itself. And then we can continue our work. And another it's possibility to uh, calculate the position of point C from the triangle. Another kind of surveys is topographic surveys, leveling surveys, aerial surveys, and hydrographic surveys. Well, for civil engineering surveys, we just need also new the topographic surface, ground surface, for groundworks, for example, and leveling surveys are used to set benchmarks on site to level survey control stations. Leveling surveys we use for um, canalization and drainage systems construction. Well, this is all. Thank you for your attention.